welcome back. Okay, so what is the conclusion of whatever we discussed? To quickly recap, so if you have a structure like this, we want the capacitor to act as a short circuit at the frequency of interest, uh, right? And so what will be the voltage at this node? What will be the total voltage Vg? The total voltage Vg will be, I can use superposition because completely linear network. What will be the superposition of this be? We have two sources, one is VDD, one is Vi, right? So if I assume in case of superposition, I take one source at a time and de-energize the other source. Both are voltage sources. De-energizing a voltage source is essentially equivalent to shorting it. Right, let me connect everything together so that it makes a bit more sense. Right. So if I assume that Vi is shorted, what will Vg be? Vg will be VDD times R2 by R1 plus R2. And if I subsequently assume VDD is shorted, what will Vg be? This will be, if I further assume that the C is large enough to be treated as short circuit, so this will be approximately equal to Vi times R1 parallel R2 by Rs plus R1 parallel R2, right? This is assuming C is large now, right? So what is the assumption? What is the total voltage across the capacitor? What will be the total voltage that we will see across the capacitor? Let me mark the voltage in this direction, let's say VC. So what will be the total voltage across the capacitor? VC will be, again I can do superposition, right? So what will be, if I assume Vi to be de-energized, Vc will be what? Vc will be simply VDD times R2 by R1 plus R2, and this is expected because that was the quiescent voltage that we anyways wanted. Now in the now what is the effect of Vi? Again, because I am using superposition, I can short VDD. If I short VDD, R1 and R2 come parallel to each other. What will be the voltage then? Voltage across capacitor will be nothing but whatever we saw in the earlier example, will be V Thevenin by, right? V Thevenin by 1 plus j omega RTH times C. Okay, and V Thevenin in our case was Vi, right? V Thevenin for the capacitor was Vi, and if this is omega naught, if C is much greater than 1 by omega naught RTH, right, your Vc will be R2 by R1 plus R2. So as you see, if we follow the rules, right? If we follow the sizing rules of the capacitor, what we will see is that the capacitor is only holding the the DC portion of the information, right? So this is the DC portion of the information, and this is the AC portion of the information, right? So this is amplitude, or rather this is the response, voltage response across the capacitor, right? Voltage response across the capacitor at steady state. When I say steady state, what I mean is that you have your Vi is a sinusoid, you have applied the sinusoid and you have waited for infinite time, no transients we are talking about. There is no transient effects that we are talking about here. So the voltage across the capacitor is Vi by 1 plus, or rather the voltage response of the capacitor is Vi by 1 plus j omega naught RTHC, and this, the other one, this one is essentially the bias at the bias voltage that the capacitor is holding, right? So the DC bias or DC voltage, let me simply say DC voltage. So as you see, the capacitor is doing two jobs here. One is it is holding the DC voltage across it, and also it's allowing the AC voltage to go through. Okay, great. So now now that we have the biasing picture at the input side, let's redraw our common source amplifier, right? So what is our common source amplifier now? So let's go to a new page. So the common source amplifier now, at least at the input side, looks to be sorted. Right, so this is VDD. Okay, and this is RL. So seems like if I size C, R1 and R2 accordingly, right, it looks like all our problems are solved. We should be, and if we take the output, uh, uh, from this node, it looks like we are good to go, right? But the question is, are we? As it turns out, that is a slight bit of complication. The complication is again a practical one. Remember, I told you that there is a problem that you cannot have access to both terminals of a source, right? Similarly, you need not necessarily have access to both terminals of a load, because what is this RL? What is this RL? This RL might not be a actual resistor. This RL might be the input impedance of another stage that it is driving. So which essentially means that you only have access to one terminal of the load and not the other terminal that you will just connect it to VDD, right? So essentially the problem is we seldom have access to both terminals of RL. Okay, so which means that your RL is just like your source. Your RL one terminal, you can assume it to be implicitly grounded, right? And you have access to this terminal, which means you cannot put RL between the VDD and the drain of the transistor. Okay, so now what should we do? Input side we did something to figure, but what should we do with the output side? Note that the first condition, what is the first condition? The first condition is that we need to ensure that the transistor is in saturation. Right? Without that, we don't have any story to tell. Right? Without that, you cannot make the amplifier work like a. You cannot make the transistor work like an amplifier, simply because, I mean, go back to the small signal model of an amplifier. The GDS or the Y22 or the GDS has to be equal to 0. If the transistor is not in saturation, that is not possible. Hence, it's a big problem, right? So what is the, again, if we go back to our drawing boards, what is the easiest way of ensuring the transistor is in saturation? One is to say that I will directly connect the drain to the VDD. Okay, right? So then, what should we do with RL? How should I connect? RL? Because ultimately, what is the incremental equivalent of this? What is the incremental current? What will be the total current through the transistor? The total current will be ID plus an incremental current, right? Some del I, or let me say small ID. The small ID will be Gm times Vg, right? Gm times Vgs, where S is grounded, so it's basically Gm times Vg. And if you have done a good job in biasing the input side, Vg will be approximately equal to Vi. Then essentially the incremental current is still ID plus capital ID plus small ID, or let me say IDQ plus small ID. But where will this ID flow? Where will this incremental current flow? This incremental current clearly will flow into the VDD, right? Because incrementally this VDD is a short circuit, right? So this ID will, if I mark ID with the magenta color, so this ID will flow into the VDD, and whatever you do with RL, you will not be able to generate any voltage across RL, right? So earlier, how do we solve this problem? We put the RL in the path of ID. We put the RL between the drain and the VDD. So the ID had no other option but to flow through RL. Since ID was flowing through RL, it was generating a voltage proportional to ID, and we were reading that voltage out. But now, as I said, since we don't have access to both terminals of RL, we cannot put RL in the path of ID. So what is the solution? Okay, so if this cannot be done, firstly, first things first, we cannot expect to get anything out of this if drain is connected to VDD, right? If drain is connected to VDD, all the incremental current ID, right, this magenta ID will always go to VDD. So we have to, first things first, we have to prevent that. So how do we prevent that? How were we preventing it earlier? From drain being shorted to VDD, we prevented that earlier by connecting a resistor. In that case, it was RL, but in this case, let me say it's not RL, let me call this RD. I mean, nothing innovative. D stands for drain. I'm connecting it between drain and VDD, so I'm calling it RD. Okay. So now this drain, what will be the drain voltage? I mean, this is nothing but the common source amplifier with RD instead of RL. So what will be the drain voltage here? What will be the total drain voltage here? This will be VDD minus IDQ plus ID times RL. Correct? Okay. But ultimately, what do I want? I want the ID to flow into RL, right? I want ID to flow into RL because ultimately I want the voltage to develop across RL, right? So how do you think, can you suggest a way so that if not the full ID, part of the ID flows into RL? Well, one way to say is that one possible way is simply to connect the drain of the transistor to RL, right? Then one might be tempted to say that this part of this ID will flow into RL and part of this ID will flow into RD, right? So if not, I mean, earlier we are not getting anything, now we are getting something. This might be a decent solution, right? But even before jumping into that conclusion, let me now point out a important problem with this type of if you simply connect RL to the drain, right? So what is the problem? Let's start again from the beginning. Let's assume the RL was not connected. What is the voltage? So what is the voltage at the drain? The voltage at the drain is VDD minus this, right? So let's forget about the incremental ID, right? So the voltage, quiescent voltage, let me call this VD. So VDQ was VDD minus IDQ times, this is not RL, this is RD, I'm sorry, RD. Okay, so what is the voltage across RL? Let me call it VRL. What is VRL? VRLQ is equal to 0, right? If VRL is equal, now what will happen if I connect these two? What will happen if I connect these two nodes? If I connect VD and VRL, forget about the incremental current. What about the DC current? What will happen to the DC current? So clearly, some part of the DC current that was coming through this will now flow into RL, right? What is the problem? The problem is then the value of VD will drop, the drain voltage will drop, because now you are essentially loading the drain. You are essentially loading the drain voltage with RL in the biasing picture also, right? So why are you loading? Because the moment you are connecting RL to VD, you are drawing current out of that node, right? So what is the crux of loading? If you are drawing current out of a node after you have connected a load, the resistance is loading the network. So here you are using RL, you are loading your common source amplifier, right? And what will happen if you load? It will draw some current out. Whatever biasing you had envisaged earlier, right? After carefully writing out the equations, will go for a toss. The transistor might not remain in saturation if you are not careful, right? So what is the problem? The problem is RL is loading M1, right? RL is loading M1. Therefore, DC Q points will change. It is loading in the DC picture as well, right? Okay, so let's draw this. Let's redraw. So let's see what's the problem. So let's forget about ID for the time, small ID for the time being. The problem is this is loading, right? So what is the solution? So let's say I knew a priori, the voltage at VD is VDQ, right? So let's say I knew this voltage is VDQ, and somehow after I figured whatever VDQ was, right, I put a battery let me do this. So let's say I knew this voltage is VDQ equal to VDD minus ID RD. right? uh, and I figured out what the value was, and I put a battery VDQ between, in series with RL, right? So what is the voltage here now? The voltage here now is VDQ, right? So now if I connect these two nodes, what is going to happen? Do you think any current will flow through that blue line, through that blue wire? No, right? Because both sides of the wire were at identical potential to start off, right? So there's no need. Current only flows from a higher potential to lower potential in order to equalize in an attempt to equalize the difference in voltages. Since there is no difference in voltage, no current, no DC current will flow, right? Since no DC current will flow, my the quiescent point of the M1 will not get hampered, right? Okay, great. So let me make it a slightly better drawing. So what is the solution that we come up with? The solution that we come up with is identify whatever voltage VD was, VDQ, and include a battery of exactly that value VDQ. Now some of you might get angry with me and say that half the lecture you have told us that I cannot use a floating battery, then how come I am using a floating battery suddenly? You are absolutely right, we cannot use a floating battery, but now we have a replacement. What is the replacement? An infinite capacitor, right? So instead of using VDQ, what will we use? We'll use a capacitor, right? So we'll use a capacitor. Let me call this C2, and let's assume C2 tends to infinity, right? So if I use C2 and I use C2 tends to infinity, right? So what will be the voltage? What will be the voltage across C2? What will be the voltage across C2 under DC condition, right? So voltage VC2Q, let's say VC2Q, the Q stands for quiescent. What will be VC2Q? So clearly at DC, capacitor is open circuited, no current will flow. So what is this voltage? That voltage is 0. What is VD? VD is VDQ, right? So VC2Q is VDQ, which is VDD minus IDQ RL, right? So note that by putting a capacitor, we are not disturbing the quiescent point of the transistor, right? If we can ensure that we are not disturbing the quiescent point of the transistor, that is a good start, right? And the RL is no longer loading the quiescent point of your quiescent operation of your transistor. Okay, great. So what about the AC condition, right? So let's sketch the AC equivalent, right? Before we go into the AC condition, let's sketch the AC equivalent. Let's assume the gate is at VG. What is the equivalent of the transistor? The transistor is a GM, a voltage control current source. The source is grounded, right? Source is grounded, so we don't have to bother too much. On top, I have RD, right? What should I do with the other side of the RD? The other side of the RD should be grounded because again VDD, right? So this grounds. From here, I go at the drain. What do I have? I have a capacitor, an infinite capacitor. An infinite capacitor, in an incremental sense, is a short circuit, right? So the capacitor shorts. Then what we end up with? We end up with RL here. So let me use a different color for RD because that's how I have sketched it in the figure on the top. Okay. So what will be the value of this GM? It will be GM times VGS, right? In this case, hence it will be GM times VG. Okay. And from across which node am I interested in taking the output. Clearly, I am interested in taking the output across RL, right? So this is my V naught. This is V naught. Okay. So if that is the case, what is the incremental V naught? So note that in this case RL and RD are in parallel to each other, right? Since RL and RD in parallel to each other, all the incremental current GM GMVG is flowing out of the parallel combination of RD and RL, and by taking the voltage across RL, I am essentially taking the voltage across RL and RD, parallel combination of RL and RD for the purpose of this analysis, right? So V naught becomes equal to minus GM times VG RD parallel RL. Okay, and if you bias your input side properly, this becomes minus GM times VI times RD parallel RL. Okay, which means the incremental gain V0 over Vi becomes minus GM times RD parallel. Okay, so this is clearly, this is not as good as minus GM times RL, which we could have gotten if we had plugged RL in instead of RD. If we had the option of having access to both terminals of RL, and I could have plugged RL in between the drain and VDD, but we couldn't do so. And what was the replacement? The alternate architecture was to put RD between VDD and the drain, and RL is grounded, right? So and because now the current is getting shared, incremental current is getting shared between. Note that this incremental current is getting shared between RL and RD, right? Earlier, all the incremental current was going into RL. Because the incremental current is getting shared between RL and RD, we are getting a lower gain. Okay. Okay. So one final thing, let me ask you before we stop. Again, we assumed C2 to be infinitely large, right? What do you think? I mean, clearly you cannot again have an infinite capacitor, right? What do you think will be the value of C2? Or what will be the constraint on the value of C2, right? When if we have to choose a value so as to pass a waveform of frequency omega naught, right? So essentially, what I'm asking is, can you figure out what will be the constraint, or what will be the limit of C2, or what will be the constraint on C2, just like we figured out the constraint on C at the beginning of this lecture, right? So I hope you can do it yourself. I'll see you in the next lecture.